So thank you all for coming today. I think we have a lot of people internally from the Touchless project, and we also have some external people, and of course our presenter today, Vivian Shen. First off, for those who don't know, Touchless is a EU-funded project with the goal of developing the next generation of touchless haptic technology, haptic interactions, and AI. So we are a consortium of University College London, University of Copenhagen, Universidad de Navarra, so UPNA in Spain, Ultraleap, Sufferth, and CrowdHelix. Um, so we are recording this presentation today, and I would please ask everybody except Vivian to turn off the camera once the presentation starts, or you can also do it now. So I'm just going to give the word to you, Vivian, and I think your presentation would be around 20 minutes, and then there'll be time for some questions afterwards. Anyway.
So yeah, thank you so much for having me here. I feel like, there's not a ton of people around the world who are working on this kind of stuff. So it's really awesome to be able to connect with people who are also working in a similar domain, and learn from y'all as you guys are learning, trade knowledge. So yeah, thank you so much for inviting me here. Unfortunately, I didn't get to meet Martin or Tor at Kai because I was not there on the last day when we made contact. So it's great to be able to meet you online as well. And yeah, so I'll be giving my talk from Kai, but an extended version. I have like a 20-minute version that I give, at other venues. So let me start sharing my screen. Okay. Please let me know if you can't see it.
We can see it, but is it possible to turn your microphone a little bit louder?
My microphone louder. Sure. I've actually never used Teams before.
Okay.
So I'm not sure I know how to do that. I can just speak louder. Is this better?
I think I can hear fine, but I think some of the other people are having a hard time hearing. Just see.
On Teams, you can go, hi Vivian, on Teams you can go to more options, and then you can select which microphone is used. It could be from your laptop or from your external microphone or something like this. So you can select the input device.
Okay. Is this microphone a little bit better?
I think it's the same to me right now.
Yeah, I don't know. Sorry, I don't have any other ones, but I'll try to talk a bit louder. Unfortunately, my headphones just died, so can't use that.
Okay. I mean, I can hear, but I don't know about everybody else. I think we're a lot louder than you, but you're quite low compared to everybody else.
So maybe if you try to speak, maybe not shout, just try to speak close to the microphone, and the rest can go maximum on their volume.
Okay, sounds good.
Yeah.
Okay, great. All right, so yeah, like I was saying, this is a longer form version of my Kai talk, so I kept it on the Kai slides. But I added a lot more detail about kind of the software that we built out, and then also the studies themselves to talk about the actual sensations and what people felt. So yeah, so this is mouth haptics in VR using a headset ultrasound phased array. I collaborated on this with Craig Schultz and Chris Harrison, who are both from the Future Interfaces group, as well as I. For a little bit of background, I'm a second-year PhD at Carnegie Mellon University. Chris is my advisor. The Future Interfaces group is my lab. My PhD is technically in robotics, but for the last 2 years, I've been only doing HCI projects, mostly focusing in the realm of sensing and haptics, so input and output type stuff. As I'm sure all of you are aware, a large portion of haptics research is based on creating sensations on the hand. while rendering haptics to the rest of the body is relatively less explored. So we kind of wanted to look into the face, as it is second to the fingertips in terms of tactile sensitivity. And this is a graph that we took from tactile innervation densities across the whole body, which came out in 2020. And it found kind of the difference between the spatial acuity on the y-axis and the spacing between the lip, the nose. Those are all body parts that have a high density of mechanoreceptors just after the fingertips. And so we thought it'd be interesting to explore this kind of less developed, less explored area. So there is, of course, a lot of previous literature on rendering haptics to the face. So here in this video, we see 4 systems, and they utilize a wide variety of sensors and motors to create visio-haptic VR experiences. 2020, 2018, 2021, 2019, these are all actually very relatively recent systems, past couple years. So prior systems for face haptics include skin stretch actuators, vibrotactile motors, suction pads, and more. And this is on the face. They're all around the HMD, so they're not actually contacting with the mouth. And here are systems that also include mouth haptics. So that's mostly using stuff like fans, air sprays, robotic arms, and more. And this is not, of course, a comprehensive literature review. These are just some example images so you can see some of the prior literature. The previous systems are interesting, but we thought that they were lacking one or more of these key factors of expressivity, form factor, and cost. So for expressivity, we wanted a system that could have distinguishable and localizable effects. For form factor, we took into account size, robustness, integratability, and battery life. And for cost, we wanted a system that had the potential to be mass-produced for commercial use. And this is the solution we arrived at. Ultrasound phase array haptics compactly integrated into a VR headset. Ultrasound transducers can be mass-produced at cost, and ultrasound phase arrays create small, localizable haptic point that can enable a range of haptic effects. So I know we have obviously several experts in the field of ultrasound array haptics here, which is really cool for me. But for those who are maybe not as knowledgeable, I'll dive a bit further into the background of this research before I talk about this method before I talk about my research. So this is taken from Ultraleap, this graphic. But for this haptic method, an array of ultrasound transducers are fired in different phases. As the waves propagate, the wave fronts, if properly timed, will all meet to constructively interfere at a focal point above the array. And then when enough transducers are kind of focused on this one node, the acoustic pressure reflected off the skin creates a dent in our skin, and that's what we're feeling. To further amplify the feeling of the acoustic pressure, we modulate the node on or off because it's easier for our skin to tell the difference between on and off when we're using a node on the skin. And this was taken from a paper by Jingu et al. And this kind of beamforming allows you to position the dot anywhere in 3D space, so long as the node is an appropriate distance from the transducers and the timings are all exact. And we thought this would allow for more, this typically allows for more expressivity, I should say, due to the fine grain and precise control of the ultrasound haptics and the focal point. And the actual effect, I feel like, feels like a bit like a small vibrating node in the air. And you can see it with this piece of paper here. So Carter et al. Really brought ultrasound phase array haptics to the forefront of HCI in 2013 with Ultra Haptics, which spawned the Ultraleap series. And then the other picture on this slide is the Ultrino model from Upna Lab, which is the one we built upon. So thanks to those in the crowd who worked on that one as well. Now I'll be going over our implementation. So we iteratively developed a new and compact way to achieve haptics on the mouth. For the hardware, we used an Oculus Quest 2, although this technique is transferable to any virtual reality headset. It's not tied to the Quest. We had a custom PCB connected to the Ultrino driver board that was fitted over an Arduino Mega. The proof of concept hardware used 64 CAN type transducers bent at a 45-degree angle to better focus the waves onto the mouth. We measured the sound pressure level at above the device and at the ears, and we found it to be at a safe decibel level, both in front of the array and at the ears. So the transducers, the Murata transducers, have 80-degree emission cones, which is why we bent them at this 45-degree angle to better focus on the mouth. We also developed our own software simulator in Unity to be able to manually focus the beam in space. We kind of backtracked how the Java files from Ultrino were writing to the driver board itself, and then use that math to use that math in Unity to create a similar simulator type software. So here the red bar represents the average person's lips would be relative to the transducer array, and each transducer is represented as a colored sphere. The black sphere represents the focus node, and as we move it through space using the arrow keys, the transducer spheres change color according to the phase offset that they are in. We calculated those phase offsets using Euclidean geometry, relating the distance of the node to each transducer and the frequency and wavelength of ultrasound. We explored several effects, including single impulse, impulse trains, swipes on the X, Y, and Z axis, and persistent vibrations. Our haptic sensations can be felt on the lips, the teeth, and the tongue, although those all feel very different, which I'll go over later. Here's a table depicting the 6 animation types that we defined, seen here being animated on the lips. On top of these animations, we have several parameters we can set for more haptic expressivity. First is a Unity connotation of world-bound or mouth-bound haptics. For world-bound effects, the effect is tied with a VR world element, and they can be felt by moving your mouth to the object, like a water fountain. So if you move your mouth to the water fountain and you hold it there, the animation will continue to play until broken off by spatial movement. For mouth-bound effects, the effect will happen in the mouth no matter where in the world the user is. So for example, if rain is falling, and the length of the animation is determined temporally. We also have control parameters that are tunable for more expressivity, such as the modulation frequency of the note, how far apart the spatially modulated nodes are, or the amplitude of the wave. When we were modulating, we found that instead of on and off, that actually if we modulate 2 nodes right next to each other, like I'm talking about like 1 millimeter apart, it actually feels stronger because you're always having this input, but it's still spatially changing rather than just a simple on-off. So we ended up going with mostly using the modulation of 2 nodes rather than 1 single node that's on and off. And so that's the node separation that you can kind of change when you're changing stuff about the modulation. To use our full stack, you first create a VR scene in Unity. We wanted to make easily integrated software. We were kind of inspired by how in Unity, when you're creating a scene, you can drag and drop color or materials onto different objects in Unity. And we wanted to emulate that with haptics. So we created an animation API that allows you to drag and drop the haptic node script onto any object, for example, on the water stream of the fountain. And from the haptic node script that we wrote, you can preset animations from the animation library as well as set the control parameters. And so in the future, we envision something where designers are thinking about haptics at the same time when they're developing their apps, the same way they think about audio or color or material, and not as kind of a post-design, post-development addition of adding haptics. The API also includes the ultrasound array and lip collider prefab in Unity, which you attach to the Oculus headset, the OVR rig in Unity. When the lip collider collides with the haptic node, the real-world Euclidean distances are used to calculate the phase offsets in Unity and transmit them through serial to the Arduino Mega and driver board. These are what we adopted from the Ultrasound instructables with help from Azir himself, so thank you for responding to my email. And then finally, the signal is transmitted into the ultrasound phased array. Oops, those are the 3 parts for the haptic effect. This happens almost instantaneously, and the signal will continue to be transmitted so long as the collider is triggered. So we conducted a standard psychophysical perception study to determine the minimum detection threshold of our mouth haptics. We ran 8 users through this study, which we adapted from Levitt from Psychoacoustics. To find the threshold of detection, we utilized the transformed 2 down, 1 up double staircase method. The bottom staircase started with an amplitude of 7 volts, and the top staircase started with an amplitude of 28 volts, which correlate to the sound pressure levels that you can see on the y-axis of this graph. We used 3-volt steps, and at each location, we modulated the amplitude of a single impulse animation and asked if the user could feel the node. If the yes was answered twice in a row, we decreased a step, and if no was answered just once, we increased a step. After 6 up-down reversals, as shown in the circles on the chart, the test was done. And this reports things as I have to check the paper for the exact number, but I believe it's 70% confidence of finding the threshold after 6 up-down reversals in this manner. We repeated this at 50, 100, and 200 hertz on the lips, teeth, and tongue for a total of 9 trials per participant. And here's an actual example staircase from one of our participants, again with the voltages as sound pressure level. Represented as sound pressure level, which we just did a simple calculation to change that. Here are the varying minimum detection thresholds that we measured from our perception study. So at the lips and teeth, the detection threshold was nominally lowest at 50 hertz. And on the tongue, the effect was nominally strongest at 100 hertz. Although, as you can tell from like the standard error, there was some uncertainty there. And the lips had slightly lower average detection thresholds, which we anecdotally also found to be true, because when we did the mouth haptics on herself, me and my advisor, we definitely thought it was much easier it was definitely easiest to feel in the lips and quite a bit harder to feel on the teeth and the tongue. We also conducted a spatial acuity study where we placed 2 spaced apart 500 millisecond impulses, also at the lips, teeth, and tongue. We found that there was essentially 0 spatial acuity on the teeth and tongue because there was 0 converged staircases from any of our participants. On the lips, those with successful staircases converged around 9 millimeters, meaning that those users could pretty much consistently distinguish nodes that were at least 9 millimeters apart. Next, I'll be going over our example scenarios. So based on our library of haptic effects, we designed 3 example scenarios with 4 interactions each, creating 12 unique scenes. We experimented with a variety of durations, positions, generation rates, modulation frequencies, and our interactions span the 6 animation types that I described earlier. And I'll be showing a brief clip of every interaction, so no worries about reading this whole table. First up, we have the haunted forest scenario, where the user starts by walking through some spider webs. As the user passes through the spider web, an X swipe is animated, simulating a spider web being drawn off the face. I didn't include audio in the presentation because I didn't want it to distract from what I'm saying. But if you watch the video on YouTube, on our channel, or on our website, you can actually hear the haunted forest noises and all the other noises. In a clearing, a spider jumps onto the user's mouth, which generates random impulses that travel toward the right, simulating an insect scurrying around the face. This one was a huge favorite with everyone we tried it on. Afterwards, the user must shoot a flare gun at a spider, exploding it into goo that splashes the user. This too utilizes random impulses centered on the mouth and at a higher frequency. Finally, there's a large boss spider dripping with venom that rains down onto the user, manifesting as random Y swipes on the mouth. Next is a school simulation to showcase various real-world objects, such as this water fountain. When users lean in and their lips meet the water stream, they feel a series of rapid vibrating impulses. Later, they go into the break room where they sit down to drink some coffee. This utilizes animated Z swipes to simulate liquid entering the mouth, with the haptic node literally translating into the mouth with our software. They can also take a puff of a cigarette, which manifests as a high-frequency persistent node where the cigarette meets the lips. Finally, the user brushes their teeth before returning to work. Upon lifting the toothbrush to their mouth, our system animates a haptic as a motorcycle racing game. Our system animates a wind effect by rendering 2 outward moving swipes on the lips. When I say 2 outward moving swipes, we actually alternated the node on which side of the lip it was while moving outwards, because as I'll explain later, one of the limitations of the device is that I made the software only able to render 1 node at a time, so we can't actually do multi-node effects. On the track, there are boxes that break apart upon collision. When this happens, we generate a single impulse on the user's lips lasting for 500 milliseconds, as if a piece of the box hit them in the face. It then starts to rain, which manifests as a series of slow impulses that hit the mouth in random locations. And then puddles are now left on the track that can splash the user, which our system haptically renders as a series of rapid, random location impulses on the lips. Using these example scenarios, we conducted another user experience study to measure our device's impact on virtual reality experiences. We ran 8 users through the study, The procedure involved playing the interaction twice, both with and without haptic mouth feedback, and we alternated whether with or without feedback played first per participants. So we counterbalanced that. After each interaction, we had the user answer a 6-question Likert scale survey about the experience regarding 6 different categories. For those that aren't familiar, the Likert scale ranges from strongly agree, disagree to strongly agree. And we used a 7-point scale that we assigned point values from -3 to 3 or 1 to 7. Same thing. After each scenario had been played, we had participants fill out a post-study 4-question survey directly comparing with and without haptic feedback for realism, immersion, fun, and preference. We also had participants fill out a post-study 22 haptic experience question survey, which I'll explain more about later. First, here are the results of the inter-trial survey. As depicted in the bar graph, with mouth feedback dominated every category of realism, localization, tactility, reaction, immersion, and visuohaptic match. Obviously, tactility had the farthest contrast in that the mouth feedback far outweighed any ghost tactile sensations that users felt without haptics. There was also a large difference between realism and localization of the interaction, the smallest contrast was in immersion, where users still felt more immersed with haptic feedback. There's just less contrast with no feedback. And these questions were adapted from Gonzalez, Franco, and Peck. In the post-study survey, users were asked to directly compare with mouth and no mouth feedback for the overall experience, and haptic feedback again won in every category of realism, immersion, fun, and preference. At the end, 0 users preferred no mouth feedback. And these questions were adopted from Feng et al. As mentioned before, our second post-study survey was meant to evaluate the 5 dimensions of the haptic experience. These are, as defined by Kim and Schneider, harmony, which asks whether the haptic feedback fits with the other senses; autotelics, which asks if the haptic feedback feels good as an isolated experience; expressivity, which asks if the various haptic effects are distinguishable; and immersion and realism, which are self-explanatory. We adopted a 22-question survey from Satyamurthy et al. That seek to evaluate these categories. And here are the 22 questions. I've linked it in my paper if you want to actually see what the individual questions are, but here I've kind of broken them down by these categories that I just explained. Our results show that mouth haptics scored higher in the autotelic and harmony categories rather than relative to the other categories. And so, you know, that means the haptic feedback fits well with the visual component and was desired. It was something that felt nice. The immersion and realism categories were pretty neutral in terms of how they scored, while expressivity was our lowest, which is one of the limitations I'll discuss later. But first, here's a fun video of our participants using the device. Some participants would react to the physical haptics. So with the spider on the mouth demo, when it was just VR, you know, they were like taken aback a bit when a spider jumps onto your face in VR. But we had, I believe, 2 or maybe 3 participants actually hit like themselves in the face trying to like get the spider feeling off their mouth. So I was able to get one of those on video, and it was very funny. I was very worried, you know, they might break my device by hitting it, but it's fun to see them react to the haptics. And then the second person, he was saying that like when he's like putting things to his mouth in VR, which I know that I've done a lot in like games where like you eat or drink to heal or those kind of mechanics. It's really difficult to actually know when it's near your mouth because you lose sight of it once it gets too close. So the haptics helped him distinguish when he was like actually putting the cigarette or the mug to his mouth, or like the water stream. And then the third person is just saying that it feels so interesting. You know, your lips aren't typically stimulated in everyday life that often, or we don't notice it because it's a lot of subtle things like wind or like eating. So it's interesting having that as the main feeling. And finally, here's my final part, which is the discussion section. First, I'd like to talk about power consumption. As virtual reality becomes increasingly untethered, we want to ensure that any add-ons can be powered directly from the Oculus headset and not require any additional wiring setup. So using our minimum voltage threshold of 20.1 volts as calculated in the perception study, we found that our device, when active, used 2.71 watts and used 0.3 watts when on standby. So if we'd assume our device generated a 1-second haptic event every 30 seconds on average, that's an overall power consumption of 0.38 watt-hours. So the Oculus Quest 2's battery is rated for 14 watt-hours, which means that our device will only use 2.71% of the Oculus battery per hour. And with further power optimizations, we believe we can drop this to just 1%. So we think that this device's power consumption is already feasible for real-world use if people were to prototype further on this kind of method. Unfortunately, as with any system, there are still limitations to our device. Although we're able to create a more compact device, it's still 15 millimeters thick and quite noticeable. An added con of this is that because it's so thick, the ultrasound transducers are closer to the mouth, making it more difficult to focus the ones that are further away or on the edges due to the close range. This also means that the weight of the board was about 107 grams, adding almost 16% to the weight of the Oculus and making it quite difficult to bear for long periods of time. Right now, as I mentioned, our software is only capable of rendering one node at a time. Although this is not an inherent limitation of the haptic method, as I'm sure you all know, this was a limitation that we encountered when I was designing, my application suite. So this currently limits our mouth haptic expressivity, especially because the mouth is still less sensitive to haptic feedback than the hand. So subtle animation differences with just one node can often be unnoticeable. We also ran into some accessibility issues in that 3 out of our 19 participants that we brought to the user study felt that they were unable to actually feel the mouth haptics, and we had to dismiss them. And part of the reasons we believe this is because our biggest limitation that I struggled with a lot was the calibration difficulty. So we realized that we couldn't just build one solution because everyone has kind of different facial geometry. Everyone's mouth is a different distance from the headset. So we decided to do manual calibration per participant. And to do that, we were moving the node in space through XYZ space with millimeter steps. So as you can imagine, there's a lot of area to be explored, and we're moving the node very minimally because it makes a huge difference. The node is so small that if it's not really centered on the lips, if it's even just like a little bit off, you're not going to be able to feel it. So it was pretty slow going, and it was pretty inaccurate for whether we calibrated perfectly to the center lips or not, especially because these people had never really felt this sort of haptic technology before, so they didn't know what they were looking for. For me personally, when I was calibrating on myself, because I knew what it was supposed to feel like, and so I knew that like if it felt like a little bit like this on the left side of my mouth, that means it needs to be centered and it needs to be like brought forward. So to calibrate on myself or like my advisor took very little time, but for people who are new with the technology, it took a lot of time and it could be inaccurate. And we believe that's one reason why some of our participants were like they couldn't feel it. It wasn't necessarily maybe because they couldn't feel the effect, but rather that we couldn't calibrate it well to their face and just never really got it dead on. So for our future work, we hope to automate this calibration process using rangefinders or computer vision of some sort so that we know where the lips are relative to the array and we aren't just guessing based on eyeballing. We also ventured into building a new iteration of our hardware using much thinner, more compact transducers that will reduce the board thickness to just 2 millimeters. The picture transducers are less powerful, so we use 256 of them rather than 64. We found that when we group these into 4s, we could create comparable sound pressure levels to a CAN transducer when we run all 4 of them in phase. Unfortunately, with these transducers pointing face down, it was impossible to focus them on the mouth. As you can see, they're clearly pointing like down here and not onto the mouth. And that's why we ended up not being able to go make a working prototype of this. So you can feel the haptic node directly underneath the array, which feels good, but that's not where our mouths are. Our mouths are kind of shifted at an angle. So a new geometric configuration will need to be designed for them to be able to focus a haptic node on the mouth. Finally, to further improve haptic expressivity, we could add compute for multiple nodes and do a more exhaustive search of the potential haptic effect space for our future work. So in conclusion, we presented a novel implementation of mouth-based haptics in VR using an ultrasound phased array. We believe that mouth haptics can be an engaging addition to consumer VR systems, and I know that I'm very excited for future developments in this field. So thank you all for coming to my presentation, and thank you all again to everyone who enabled this research with your own prior related work, and thank you for inviting me here today to talk to you.